Thank you. Welcome back to ME 760 Engineering Analysis 1. So we continue the same business of the taxonomy for the differential equations and defining what do we mean by degree, order, homogeneous, inhomogeneous, and so on. So let's continue this part. Then we will start looking at the first order differential equation, how to solve them. But today's lecture, excuse me, in today's lectures, just will give the conditions for the existence and uniqueness for the solution. So today's lecture will be a little bit, for this part of solving the first order differential equation, looking for the uniqueness and existence, it will be a little bit abstract. So from next lecture, it will be more fun to look at the solutions. So last lectures, we looked for, I think we stopped at the singular solution. Do you remember what's the singular solution? So it is a solution not derived from the primitive solution. And we look at the envelope, which was a parabola that has all the solution in linear format, and all of them will form something like an envelope like this. So all your solution come across like this, and so on. So this is all the solution, but the envelope form another solution, which was something like, I think, x squared over x squared plus 8y. This was the solution for the envelope for the solution. So if you have a solution that's not derived from the primitive solution, which is linear in this case, we call it a singular solution. So let's now continue the same business that we did. So we knew that ODEs, ordinary differential equations, may have no solution. For example, the equation dy by dx all square is equal to 1. So this solution, has no real solution. Because if you take the square root of both sides, you will get dy by dx equal to what? This is -1. Equal to what? The square root of -1, which is I, and this is not a real solution. Excuse me. Maybe you will have only a single solution. For example, the dy by dx equal to -y. So what solution satisfies this? What do you think? A function that if you differentiate it with x, will give you, and you take the absolute value, will give you the absolute value of the same function. There is no solution but y equal to 0. So this is the only solution for this differential equation. So if you have a set of all solutions to ODE is the complete solution. So the set of all solutions, we call it the complete solutions. So if you also look for linear equations, linear equations will have no singular solution. And we stated clearly last time that what type of equation has the singular solution? Last time we stated what type of equation? Nonlinear. And we said that not all the nonlinear equation will have a singular solution, yes? But usually the singular solution is a characteristic of the nonlinear. But we are talking about linear now, so those will have no singular solution. And the standard form for the nth order differential equation will be yn. So this is not y to the power of n. This is y, the nth derivative of y. So yn plus pn minus 1 as a function of x, yn minus 1 plus pn minus 2 as a function of x, yn minus 2 plus p0 of x, y equal to a function r of x. And let's call this star. So this is nth order linear differential equation with variable coefficients. So the coefficients are what? Are not constants. They are variables here. So if you have your r of x equal to 0, this equation is what? The equation is homogeneous. Otherwise, the equation is what? Inhomogeneous. And usually it will have the general solution you will have two main parts of the solution. So your solution y as a function of x will have the solution for the homogeneous equation plus the solution for the inhomogeneous equation. Okay? Solution for homogeneous equation when r of x equal to 0, we will see later on the class here that it has Cj y homogeneous j as a function of x, and this is goes from j equal to 1 to n. You will have n in linearly independent solution. So each one of those yh, let's say yh1, yh2, yh3, yh4 are a solution, is a solution. Each one of those, if you substitute here, it will satisfy the differential equation, and the linear combination of those solutions will also form what? A solution for the differential equation. So if you have y1, for example, cosine alpha x. So if you substitute here with cosine alpha x and it gives you equal to 0 for the homogeneous equation, this is the solution. Maybe the n-harmonic of cosine alpha x, let's say cosine beta x, cosine zx, cosine blah blah blah. So when you do the linear combination of those, this will be a solution. And now this is the solution for what part? Homogeneous. Then you will have a particular solution for the inhomogeneous part here, and we will see later on the course here how to solve this equation. So again, the y, h, j of x are the n linearly independent solution for the corresponding homogeneous equation, and y p x is the particular solution and both of them will satisfy this equation. Equation star. Again, any nth order ODE can be expressed as a system of first order ODEs. So our equation here, we can represent yn as equal to r of x minus all the other terms, the rest of the terms. So y of n is just, you can represent it as this. So this will be just a function of x and y. A function of x and y will be, let's say, r of x is a function of x, and this is just a function of x and y, yes? This is r of x is a function of x, and this part is a function of y, yes, y and x. So you will have a function of x and y, and y prime, y double prime, up to y n minus 1, which is this term here. So if you move all the rest of the term except yn to the right hand side, you will get a function of x, y, y prime, y double prime, up to yn minus 1. Then this is given from the definition of the higher order or nth order differential equation, linear differential equation with variable coefficient. So let's assume that y1 of x, this is not the derivative. y1 is just, we call it y1. It's a variable, dependent variable named y1. We will make y1 of x equal to the original dependent variable y. So we will name y as y1 of x. There is nothing here that. So if we get, this is y1 prime. I'm sorry. This is y1 prime. So we will have another variable y1. If we differentiate this y1 prime, it will give us y. Then y2 prime is just y3. This is y2. Let me. Oh, I made a mistake here. So we will let y1 of x equal to y, y2 of x equal to y prime, y3 of x equal to y double prime, up to yn of x equal to yn minus 1. So all what we do here is just making something like, we will call it like as if you are transforming your coordinates. So this is change of variable. All what you will do, you will come to the original ODE, you will name the variable y as y1 of x, the variable y prime as y2 of x, y double prime, you will name it y3 of x, ynth of x is just the n minus 1 derivative for y. This is just a change of variable. Why we are doing this? Our goal is to try to transform a single equation, nth order differential equation, to a set of linearly coupled differential equation of the first order. So this is an nth equation, nth order equation, differential equation. Our goal is to decompose this and make it a set of n linearly dependent first order differential equation. So why you will do this? It's very easy to solve first order differential equation. It's just dy by dx equal to f of x, for example, f of x of n y. So it's very easy to solve a first order differential equation. They are, let's say, a set of, let's say, nth of those equations, and they are linearly coupled. So we will see later in the course how to solve those. So in order to do this transformation, we will assume that, okay, the variable y in the original formula is just y1. And the first derivative of this variable y is y2. Second derivative is y3, up to n minus 1 derivative is yn. Then now, equation number 1, we'll call this equation number 1. We'll see equation number 1, what equation number 1 will be here. So y1 of x equal to what? Y. So what's y1 prime? If you differentiate this, it will give you what? Y prime. What's y prime from here? Is equal to what? y2. And what's y2 prime? Equal to what? y3. And what's y3 prime? y4. And you will go all the way down to yn minus 1 prime. And this will give you yn. And then yn prime is equal to the function fx and y and y2 and yn. So now I obtained a set of coupled, a set of coupled. Do you know what does mean coupled? Mathematically, what does it mean? Coupled mean this equation has a variable that's given by a second equation or a different equation. And this equation has this variable y3, which is given in a second equation or third equation. And this equation here, y3, y4 is given here, and so on. So they are linearly coupled equation. It's like what? Like this. 3x1 y1 equal to z1, for example, and then you have, or let's make it y2. Then 2x2 equal to z1, and 3z1, let's say x1 equal to y2. So those are equations, and they are coupled equation. Why? Because in order to get y2, you have to solve this equation. Yes? And in order to get z1, you have to solve this equation. So you have to solve the three equations simultaneously together. Do you understand, guys? So this is the same. You cannot solve this one, the first one alone, and you say, okay, I will solve it alone. Why? Because this is dy1 by dx equal to y2. What's the value of y2? You have to solve this equation to get y2. But in order to solve this equation to get y2, you have to know what? y3. So you have to solve this equation to get y3, and so on. So you have to solve simultaneously those equations. So this is a set of coupled, it's called a set of coupled simultaneous ODEs. We can write those ODEs as dy by dx is some matrix A of y, A of x operated over y plus g of x. So this is just y prime. So how we will write it now? Here is the operator d by dx. And what's the y vector here, from here? It's y1, yes? y1, y2, y3, y4, and so on. Of course, we can remove this one because it does not have the derivative on it. It has just the definition of y. So this is what? y1, y2, up to yn. Actually, this should be n minus 1 or n. We do not have n plus 1, so this should be n minus 1. Because dy n minus 1 by dx will give you what? Or wait, no. This is the definition of y. Where is yn? I define it here. Oh, this is here. Okay. Yn is the yn minus 1 for the older equation. So if you differentiate dyn by dx, this will be dyn minus 1 by dx, which will give you what? dyn of x by dx equal to what? du by dx yn minus 1. This will give you what? Yn. Did you understand this, guys? So we still, this is n. This is correct. So this is y1, y2, y3 up to yn plus the j function here is 0, 0, 0, 0, 0, 0 up to r of x. So what we will put here, look at this equation. So y1 prime equal to what? y2. Yes? So we will not have a y1. So we should have here what? 0. Then we should have what? 1. And the rest will be what? Then in the next one, we do not have what? y1 and y what? 1. Yes? And the rest is 0 here. Then we will have what? And the rest is 0 here. Yes? And the last one we will have what? So we'll have minus b0. Yes? Minus b0 and minus what? b1 minus b2 up to what? Minus bn minus 1. Yes? Multiply it here. d by dx for yn, it will give you what? The nth derivative. And the nth derivative, we knew from the equation that I just erased, it was here that this is what? y1 multiplied by what? b0 minus, yes? And this is plus what? Plus r of x. We brought all the terms here. So r of x minus the rest of the terms. Okay, guys? So this will be just a matrix that will have everything is what? Is 0, but the two diagonals here. So this is a diagonal with all zeros, and this is a diagonal with all 1, but the last term here is bn minus 1, and this is bn minus what? 2. Okay, guys? Okay? Later in the course, we will see how to solve those equations, and you can solve those numerically again using the same technique that we used to solve for the eigenvalue problem or whatever matrices method that we took it during this course. Okay, guys? So now we succeeded in transforming an nth order differential equation with variable coefficient to a set of linearly coupled differential equations with what? First order. All of them are first order. So it is important now to look at how we will solve a first order differential equation to be able to see how we will solve a system of equation like this. Again, during this today's lecture, we will not be able to do any of these today, even 3 or 4 lectures ahead. We will, I think, maybe in 3 or 4 or 5 more lectures, we will be exposed to the solution for simultaneously coupled differential equation like this. But I'm just giving you a heads up. So now let's look for the first order differential equation. And again, today we are not going to show you guys how to solve first order differential equation. Rather, we will look at the uniqueness and existence for the solution. So if we look at first degree ODEs. What do we mean by first order, first degree? Is it linear or non-linear? Linear because it is what? Because of the order or the degree? Because of the degree. So the degree, first degree means a linear equation. So the general form for a first order linear equation would be just, this is dy by dx equal to f, y, and x. And if it is linear equation, this means that this is p of x, y of x, plus g of x. So if you want to write it in a more general form, dy by dx equal to or minus b of x, y of x equal to g of x, something like this. So usually this is the form for a first order equation. So now most ODEs can be solved only with numerical techniques. However, if you will use numerical techniques, they are of no use if you do not have solution. If the ODE has no solution, or if it has multiple solutions. So we need to determine under what conditions the ODE has a solution or not, and if this solution is unique or not. What do we mean by unique solution? It's a single solution. So usually most of the ODEs that you will find in engineering or physics or science or whatever, they will have numerical solution, the majority of the ODEs. Few, for example, classes will have no solution at all. So, and if the ODE is, for example, highly nonlinear, you will not be able to solve it analytically. What do we mean by analytically? To get a form, for example, y of x equal to certain function f of x, for example. So you might not be able to solve it analytically, so you have to solve it numerically. So before you go and solve it numerically, you have to check whether it has a solution or not, and if it has a solution, whether it is unique or not. So we have to look for this, and we see under what condition under what conditions does the initial value problem, and again guys, when we say initial value problem or boundary value problem, means that the ODE has an initial value. Let's say you are talking about first order differential equation that changes time. Then you said that, okay, at t equal to 0, the value for y of 0 is equal to something. Okay, so this is called initial value problem. If you are talking about solving the differential equation inside some domain or a boundary, let's say we are solving heat transfer equation inside a wall, for example, and this wall will have dimensions, so it will have x equal to -a to x equal to a. So we have to specify the temperature at both boundaries and at initial time. So this would be called initial value and boundary value problem. Initial value because you have to specify temperature at the start of the measurements. Let's say you have a clock and you want to say at t equal to 0 what was the initial temperatures, and you have to define temperatures on the what? On the boundaries of your problem. So this is called boundary value problem. So we want to see if under what condition does the initial value problem y prime equal to f of x and y with the initial value y at x naught equal y naught. So we'll call this equation number 1. So we want to see if this have a unique solution or not. So does it have a solution? Does it have a solution, and if yes, does the solution is it unique or not unique? So in this case, this is the criteria for checking for uniqueness and existence, and I will give it here without proof. And this part is not in the book, so maybe I will give you the 2 or 3 pages from the other book that I use, so that if you want to look at it, you can look at it, for example. So the existence theorem. So if the function of x and y, so this is y prime equal to certain function f of x and y. So we will look at this function. If this function f of x and y is continuous at all x and y in a domain R, and this domain is given by x minus the initial value x naught is less than or a, and y minus y naught, which is the initial value for y, is less than b. So if the function f of x and y is continuous in this domain given by the x value is x minus x naught less than some constant a, and y minus y naught is less than some constant b, and it is also the function is continuous and is bound in R such that y prime is equal to the absolute value of f of x and y, and this is less than some constant k. So if this happens, if this is satisfied, if the function f of x and y prime equal to f of x and y with initial value, if this function is a continuous in the region R between x minus x naught less than a and y minus y naught is less than b, and also it is bound with this is the bounding condition, that y prime equal to the absolute value of f of x and y is less than some number. So we will say that 1, this is 1, we will say that 1 has at least one solution y of x in the interval x minus x naught less than or equal to the minimum of the bound value for x, which was a. This is the bound value here, a, and b over, this is k, and k here is what? What's k, guys? Yeah, so it's what? What does mean derivative? If you plot something, slope. So k is a slope. Okay. So this is the existence for the solution. Is it unique or not? So this is the uniqueness of the solution. So the condition for uniqueness of the solution is if the function f of x and y and the absolute value of its derivative, let's say, was y, df by dy, are both continuous again and bound in R, y prime is equal to f, and this is again less than k, like the same condition here. But the second condition is the derivative of f with respect to y is less than some number m for all values of x and y. All values of x and y in the region R, then one has a unique solution. Solution in the interval x minus x naught less than or equal to the minimum of a and b over k. So those two conditions for the existence of solution and uniqueness of solution are sufficient condition, but they are not necessary condition. What do we mean? Sufficient means if you have a solution, if you have an equation y prime equal to f of x and y, let's say. If you have the function f of x and y is continuous in all x and y in the region R, where R is given by these two bounds, x minus x naught less than a and y minus y naught is less than b, and the bounding condition is just y prime is less than certain number k. So, and the uniqueness condition is also satisfied for the function f of x and y. This indeed indicate that you have what? You have a solution, and this solution is unique. but is not necessary. So there is other categories of functions f of x and y does not satisfy those two theorem, but still they have solution, and the solution is what? Is a unique. So this is why we said it is a sufficient condition. Yes, if you satisfy both, you will have one solution, or you have a solution, and this solution is a unique solution. But it's not necessary. So maybe you will have functions f of x and y that do not satisfy those two conditions, and they are still have a solution for the differential equation, and this solution is what? Is unique. So this is why we call this is sufficient condition for existence of unique solution, but not necessary. Did you understand, guys? What do we mean by what I write here? So let's look at what does it mean graphically. So we just put the two conditions here, but we want to know what does it mean graphically. So let's look for the first case where the bound or the limits or the borders of x, a here is less than b over k. So if this is y and this is x, and then you have here is point x naught, and the initial value is y naught, and this is the region R that we talked about. So this is the region R, and this is x naught plus a, and this is x naught minus a. So this is the a borders for you here, and then this is y naught plus b, and this is y naught minus b. This is the borders for your y direction here. Then the k, which is the slope, if you take the absolute value for the slope, for example, this is a positive slope here. So k is greater than 0, and this is k is less than 0. It's less than 0, and your solution, we stated that your solution should be in this region here, that you have a solution and a unique solution in this region, which is what's the condition for where it is? The x minus x naught is less than the minimum of a and b over k, and this is the solution y prime equal to the function f, and it is less than or equal to the slope here. So let's assume that this is your function y of x, which is the solution for the differential equation. So we saw here that the solution y of x is inside the region R, which is bounded by, from the x location here, is bounded by x naught minus a to x plus a. So this is the case where a is less than b over the value of k here. Let's look for the other case. Where you have a is greater than b over k. So if you have a is greater than b over k, this is x, this is y again, Again, this is x naught plus a, x naught minus a. This is y naught minus b, y naught plus b, and this is y naught. Now, in this case, x naught this point here is x naught minus b over k, because here we said that a is greater than b over k. Yes, guys? Let's assume that a is equal to 3 and b over k is equal to 2. Okay, guys? A is greater than b over k, 3 and 2. So x minus 3 will be this point, x naught minus 3 will be this point, x naught minus 2 will be this point. And this point will be x naught plus b over k, which is x naught plus 2, and this point will be x naught plus 3. Did you get it? So if a is less than b over k here, and here is your a is less than b over k. So this is your bound for the problem, and b over k is some way here, but you're still inside your region R. And R, I told you that R is bounded by what? X minus x naught is what? Is less than a, and y minus y naught is less than what? B. So your region R is this region, the barrel, the rectangle here. Okay, guys? So this is why if A is less than B over K, I do not care about the region outside the region R, because I am interested in looking for a solution inside this region R here. Okay, guys? So my solution is in the region R. I will have only a solution if my function y of x, which if you differentiate it will give you y prime of x, which is equal to f of x, is less than this number k, which is here the absolute value here. This is if you have a slope, this is a negative k slope, and this is a positive k slope. Okay, guys? Now, if my region or region R is less than b over k, now I have a situation that this is the negative k slope, this is the positive k slope. Again, I will have the solution in this region here. But what happened is, if your function y of x, the solution for y of x is like this, now if you get outside x naught minus b over k, you get a solution what? Outside the domain of your solution. Yes? You will get a solution y of x outside the domain of your solution, which is x naught minus b over k. Okay, guys? And this is what we said, the solution is given by the minimum of a and b over k. Yes? My solution x minus x naught lies in the minimum of a over b over k. What's the minimum here in this case? If you have a is greater than b over k, so the b over k is the minimum. So my domain for the solution will be just this region. Will be here in this region here. Yes? So in this case, if you have a solution here, it is outside your what? Your domain of solution here. Okay, guys? So those are the two conditions or two cases. Next time I will give you two examples about first order differential equation where you will have a unique solution, and the other one you will have no solution in certain zone and a solution in outside this zone. So it will be the application of those two conditions here. So I ran out of time, so next time I will give you those two. Then we will look at how to solve the first order differential equation. This is highly abstract and highly mathematical, so I do not expect that you will fully understand it, but at least to show you why we are solving, while we are solving the differential equation, we have to keep in mind that before you start solving the equation, does the equation has a solution or not? And if yes, it has a solution, is it a unique solution or not before you start doing anything? Because maybe you will start looking for solution, and from the beginning, the differential equation does not have a solution. Okay, have a good day.